I mean, this will be a little bit, I mean, tutorial type of talk on coupled cluster grids function. I mean, that's what Emmanuel and Dominica asked for, and yeah, I will. I mean, try to provide, I mean, little bit more details of the, I mean, coupled cluster grids function solver. So some relevant theoretical details, I mean, just to motivate on this coupled cluster grids function solver, and then yeah, some on the performance of this type of solver, and I mean, mostly focusing on the fact where it fails, and what are the ways to improve on this solver. So first is that the I mean, motivation for quantum embedding theory, which is I mean, I do not have to I mean, emphasize more in front of this audience, but I will like to just I mean, point out a few things which pertain to this particular kind of solver development, which is like for material, I mean, quantum embedding theories are developed focusing on the fact that one can develop just a single framework which is suitable for various strengths of correlation, let's say strong correlation in the Mott regime, etc. But what sometimes is neglected is that I mean, there is a class of material which is not per se strongly correlated, but I mean, they are often categorized as weakly correlated, like organic semiconductors and other molecular crystals. I mean, they, even though they are weakly correlated, their physics is quite rich, and often one requires to estimate like very accurate. I mean, to estimate various quantities very accurately for those materials. For example, I mean, the energy gap between different polymorphs of molecular crystal is pretty minuscule, and often different polymorphs show very different properties, and it's very necessary that one evaluates this very accurately. And also various transport kind of properties of those materials. I mean, is pretty tricky to and also yeah. So that's why I mean that's why it's I mean, it's important that important that one puts some focus on these materials as well. I mean, the kind of solver we will be developing should be useful for these classes of material. And in this presentation, we will mostly analyze with real materials how our solver perform with this particular embedding theory. And another motivation is that to apply this solver for molecule as well. For molecule, I mean, embedding theory is not is not generally used. I mean, but apart from Dominica's work, I would say, and very recently DMET type of works. I mean, for molecule as well, one can think of using using embedding theory because of the fact. I mean, here I have shown up. This is like a structure, porphyrin kind of structure, where there are two metal center within an organic backbone, and one can just focus on this metal center I mean, as an where one can use some high-level method, and for low-level method for the organic backbone. But for molecule, how my point of view is that, is that, we often demand very accurate energetics for molecule, and for a finite non-periodic system, it is very hard to reach convergence with respect to a particular choice of the embedding region. And therefore, so this accurate energetics is very hard to achieve. Because the boundary is often is not very clear, and molecule is only useful for the fact that it can be a very good test bed for embedding theories. Because of the finite size, and it can be tractable. Small molecular system can be tractable, and one can study like very rigorously for various quantities. And lastly, theories can be used for molecules just for some local magnetic moment and for some spectra. Spectra meaning that where only one can focus on the valence region. So self-energy embedding theory in brief, it's a finite temperature theory based on Luttinger-Ward functional, and where I will not go into the details. Based on Luttinger-Ward functional, which features in the definition of grand potential, and Luttinger-Ward functional consists of various skeleton diagrams in terms of G, total Green's function, and Bayer interaction. This part is very important for this theory. And self-energy embedding theory, what self-energy embedding theory does is that it divides the system into two parts. One is a local part, and another is and there is this blue non-local part. And this non-local part it is considered as weakly correlated, and this local part is strongly correlated. This phi in self-energy embedding theory is expressed like this, where we first estimate this total phi for the total phi that is for the entire system with weakly correlated method, and then phi for the local part via some strongly correlated solver like ED or continuous time quantum Monte Carlo, and then we subtract any double counting part with the weakly correlated method. And here one important point is that when we divide this local and non-local part, there is a term in the Hamiltonian which takes into account the interaction between the strong between these two parts of the system. And here in this cartoon, I have shown. This small rectangular box is our local part, and it interacts with the rest of the system. And this interaction is a frequency dependent term. It's called hybridization, and this term is hard to deal with usual solvers. Therefore, we need to discretize it. The way we discretize this is that the system is in equilibrium with respect to a mean field. We consider the system is in equilibrium with a mean field path, and this leads to a system path coupling term in the Hamiltonian, and that way we get this Hamiltonian. This is called impurity Hamiltonian. Then And then, in this slide, I just want to mention some difference of the self-energy embedding theory in comparison to, more pop or some, let's say, some rival theories like GW plus DMFT. And I showed in the previous slide that self-energy embedding theory is based on functional called phi functional, and GW plus DMFT or eDMFT is based on so-called psi functional, where one major difference is that one uses some screen interaction W as opposed to bare interaction V. And here, I'm skipping this part. This difference. I think it's fairly known, and there is a difference with respect to the embedding condition and the hybridization term used in self-energy embedding and GW plus DMFT. Here, the primary focus is that because of the consideration of bare interaction, we can use quantum chemistry methods as solvers. And by quantum chemistry methods, what I mean here is that mostly wave function based quantum chemistry method. There is another class of method which is density functional based. I will not consider that. Those methods, but I will just consider wave function based quantum chemistry method. And yeah, and so let's proceed. So among the wave function based density, wave function based, quantum chemistry method, what is considered exact in the non-relativistic theories is exact diagonalization. And here is a small, okay, here is a small presentation where why we need some solver other than exact diagonalization. This is a study done by Xianan and Sergei Domincan Emmanuel. So that is for strontium vanadate type perovskite, cubic perovskite. So for this system, what they have found is that with this, they have considered these three choices of impurities and tried to improve over the self-consistent GW spectra, and they were successful in most part of it, but failed to reproduce a satellite spectra near the Fermi region. And among the various reasons why this cannot be produced, one is that they could not consider some more impurity orbitals in their choice. So, for example, the lack of 4D orbitals in the impurity, that may explain the appearance of this type of satellite spectra. And this study could not be performed just because of the fact that ED cannot handle that many orbitals. So what is necessary is that somewhat cheaper method that can deal with more orbitals. So couple cluster could be used as one of such impurity solver. So why couple cluster? So for that, let me provide a little bit more background of couple cluster. So couple cluster is a wave function method, based on an exponential parameterization of cluster operators. Here a cluster operator means various whole particle excitation, and here I just have shown the whole particle excitations up to rank 2, that is rank 4. So this is just singles, doubles, approximation. And the working part of couple cluster is obtained by projecting various excited determinants onto the Schrodinger equation after transforming after similarity transforming the Hamiltonian. So this is called so-called amplitude equations. And yeah, this is nothing but like if you consider the whole space as your ground space of your ground state, and the rest as your excited states, and you project out all your excited space, and then to obtain some ground state parameters. And then you end up getting these equations, and from these equations you evaluate all these amplitudes, and then you plug them back in the couple cluster energy equation to get the couple cluster energy. So this all looks very simple up until now. So but what is so great about it is that if you consider just a CI expansion, which is rather, I mean, here I've omitted some prefactors. So the CI expansion, which is just a linear expansion, and it also takes into account like various whole particle excitation up to up to various ranks, but one can easily see that because of the exponential parameterization, so it can simulate some higher order excitation, but in a very controlled way. So by control here I mean is that there is a underlying diagrammatic structure which can by which one can maintain the size extensivity of the theory. I'm sorry. So yeah, so that's how I mean it kind of captures way more physics in comparison to a CI expansion. And another advantage of couple cluster is that it includes all order perturbative terms with respect to the truncation we have used for the theory, because I mean all because if we focus on this amplitude equation which is used to evaluate all these wave function parameters, this actually analytically truncates at quartic power. So therefore, I mean there is no numerical truncation or any arbitrary truncation. So it actually encompasses all order perturbative terms with respect to the truncation we used for the theory. So then, and a reflection of this fact is in this chart. I mean, here what we have tried to show is that this green one is a convergence study of a couple cluster series, and one can easily see that at the singles, double, I mean singles, doubles, triples, and this is quadruples. And one can easily see that at the triples level, is it okay? It has almost converged. For CI, one has to go at the quadruple level. So where the convergence is way slower, and the perturbative method is usually oscillatory. And also one can see that the convergence is much slower. So because of this, I mean this better convergence with respect to the rank of truncation, so couple cluster should be a preferred choice among various classes of wave function based theories. And One last point is that here we are actually mixing couple cluster with diagram-based finite temperature perturbation theories. For example, GW and GF2. So my couple cluster has some diagrammatic, underlying diagrammatic structure, which I have not gone into the details of it, but it includes various ring exchange and ladder type of diagrams. So in comparison to GW, where ring diagrams are present in all orders, but the exchange is present only in first order. So there is definitely, there are definitely more classes of diagrams, and the ladder diagrams are altogether missing in GW. And and for GF2, only up to second order ring and exchange diagrams are there. So there is definitely more classes of diagram there in couple cluster theory. And so next is that couple cluster, as I said, is a wave function based theory, and how we map this couple cluster, this wave function to a Green's function. So for that, we use the layman representation or the spectral representation of the Green's function. And here, in this equation, we use the left and right hand okay, let me say it a bit more carefully. So the right hand side of a couple cluster wave function or the Kate part is not the adjoint of the bra part. So because of the non-Hermitian nature of the theory. So yeah, I don't have much time to go into why it is so, but because of that fact, we have to use like two different representation of the left and right hand side of the wave function. They are not orthonormal but bi-orthonormal. So we plug in these two representation of the left and right hand side in the Bryan kit, and then we get this representation of the Green's function. Here one can see that various similarity transformed quantity appears. Both for the Hamiltonian and the creation and annihilation operators. So usually in various previous works and some recent works, the way this quantity is evaluated numerically is that this inversion is cast as some sort of response equation, and therefore via this xp quantity, which is a frequency dependent quantity, and we solve for this quantity and then plug this back here, and then we can evaluate total Green's function. The problem with this approach is that this quantity is complex and therefore complexity of these equations goes as into the 5, that is the scaling of this matrix vector product that comes in these equations times the number of frequency points used for a particular calculation. And what in my experience, sometimes these equations are numerically unstable as well. So we wanted to improve upon that, and in order to do that, we took a Langsau's based tridiagonalization route, and where we first express we first express each element of the Green's function. Sorry, just a second. Let me get back here. So our primary objective is to invert this quantity. So then what we do is that we tridiagonalize this H bar, and then this tridiagonalization is given by this. And after we achieve this tridiagonalized form, we can evaluate. Green's. We can carry out this inversion analytically by using continued fraction formula, and the cost of this term goes linearly with respect to the number of Langsau's vector needed to get this tridiagonal representation. And that's how this part is completely independent of the number of frequency point used, and we just subtract the frequency part from the diagonal of this matrix. So the scaling of the whole the total calculation is completely independent of number of frequency point used. And this tridiagonalization process doesn't depend on the on a particular frequency. Therefore, there is no instability in those equations. And also, for this kind of Hamiltonian, there is no complex equation that we need to solve. So these are the numerical advantages we obtain. So now, for practical application here, I want to mention some scaling behavior of this of our approach. We first solve one in-particle problem. So the scaling of which is into the 6. And then we have to not necessarily solve, but we have to take into account some n-1 and n+1 particle problem, which scales as n to the 5, and then to evaluate to construct total Green's function, which has n square element, but we can use some triangular representation because of symmetric representation of the Green's function. So there, n square by 2 number of this n-1 and n+1 particle problem needs to be solved. So that effectively increase the cost to somewhat like n to the 7. But we can parallelize over this number of elements. And here I have shown a small code snippet, and here. What I tried to show is that the way we parallelize so far, it's based on Python multiprocessing unit, which is just some core, more OpenMP type parallelization, and it's just on one node. And here, we parallelize over number of elements, and we take these max processes as input. So, and this just depends on a number of cores available on a particular node. So more number of cores present on a node is better. But one should keep in mind that the calculation done for each element requires a certain amount of memory. And when this number increases, then the memory could be insufficient. So one should be careful in terms of choosing this number of processes. But for small enough calculation, the more number one choose, the more efficiency one will get. But one point I wanted to emphasize here is that I mean, for this CC couple cluster greens function implementation, I mean, I have used, I mean, the code that I developed is in Aquarius, and this is MPI parallelized the code itself, but I mean, but this is a particular kind of parallelization where for each, I mean. All different arrays like integral arrays, those are parallelized. I mean, those are distributed with MPI, but the distribution over elements are not actually possible. So therefore, it's kind of I mean restrictive. I mean, we could not take advantage of the full ability of the code. So this part actually could be improved. I mean, in terms of parallelization, and for larger application, it might be useful. So now, how this couple cluster greens function is integrated with self-energy embedding theory as a solver. Here, I have provided just a schematic view, but I will go into the details of each part of it. So, for first, I mean, for self-energy embedding theory, we choose an orthogonal impurity basis in which we create our impurity Hamiltonian, then compute and fit hybridization function to get Bath orbitals, then build local Anderson impurity model, and for that Hamiltonian, the quantity which is not known is how many. What is the number of particles present? I mean, particles is there for that problem. But I will go into the details of this part in the next slide. So yeah, just bear with me. And after we obtain this number of particles, then we solve for this Green's function CCSD. But this we can do only in a quasi-particle basis, in Hartree-Fock basis, or let's say MO basis, and then in the next step we transform into into the impurity basis that we have chosen, that is this orthonormal impurity basis, and then we construct self-energy using a Dyson equation, and then we assemble, I mean, various parts of self-energy to get the total self-energy and feed it into the self-energy embedding loop, which I will not go into the details again. And this is just the one loop, and or the inner loop. And again, I mean, we can, and here is the outer loop structure, so which means that after converging the inner loop, we can feed the Green's function to the weakly correlated GW method, and in just in one step manner, and can continue the loop to obtain convergence with respect to the outer loop as well. So so that's the total self-energy embedding scheme. So for couple cluster solver, both this particle sector search and this couple cluster Green's function construction step is different with respect to exact diagonalization or other methods. So I'll be discussing some peculiarities with respect to these. First is particle sector search. So why it is important? I mean, we do not know beforehand what is the correct chemical potential for the correlated problem. So therefore, it is the approach we take is that we try to get the lowest energy particle sector and assign it as the number of particles. So therefore, I mean, I mean, how we can I mean, estimate I mean, what is the lowest energy sector. So for that, what we do is that we have a given number of impurity plus bath orbital, and our approach is unrestricted, and we try to populate all these all these orbitals by electrons, and this and with this distribution we get, let's say, n number of sectors, and they are denoted as this by in number of alpha and number of beta orbitals, and then we employ unrestricted Hartree-Fock for all those particle sector or for all those distributions, and then from UHF we choose some m number of lower energy particle sectors. And this step is quite tricky because as we have considered like all possible particle distributions, they generate a problem of various complexity, and for many of them it's very hard to achieve minima, and and also converging those equations are very hard, and if one achieves some wrong minima, so that can completely destroy the cell consistency. The equations will not converge at all. I mean, if this one cannot reach the correct minima. So I have struggled for quite some time to get a good handle of this. Then the scheme that we employ right now is that we first just solve UHF equations, and then try to analyze whether this solution is stable, meaning that whether Hessian is positive, semi-positive definite, and if not, then we rotate those roots to get positive definite Hessian, and then choose that as a starting guess, and then feed it into a Newton solver or second order SCF method, and then again check for the stability, and then get the total energy. And after solving UHF, we get m number of lower energy particle sector, and from this m number of sectors, for this m number of sectors, we solve UCSD method, and from that we get we find the lowest energy one, and that's the this desired number of particles. And here, what I try to show is that when we sometimes for this truncated truncated method, because I have already mentioned, so we definitely use truncation with respect to couple cluster hierarchy in our methods, and in usual case it's singles and doubles, and that many times lead to many artifacts. And so one of these manifestation is in this particle sector search. Here, when we studied strontium manganate with the CCSD solver, so then when T2G impurity was chosen, so here what is shown is that first row is the energy of let's say the lowest energy, and the second and third is the first and second excited states. And here one can see that ED predicts all these let's say MS 3 half and minus 3 half and plus half and minus half sectors as of same energy, and it means that this is all these different MS are different spin states are combined together, or for a particular spin multiplicity state. But because of the unrestricted nature of the theory, so this can be spin broken, and this is not a spin perfect theory. So therefore, one can easily see that these degeneracies are kind of lifted in these theories, and UCCSD and UCCSD parenthesis T, so they predict slightly different ordering, and more importantly, they are not the same with respect to ED. And if we consider the example of p-impurity, so there what we have seen is that UHF completely predicts a wrong particle sector in comparison to ED, but UCCSD and UCCSD parenthesis T predicts the right particle sector. So what this tells is that so the many times this unphysical mixing of spin sectors can happen, and in many cases it actually can lead to divergences. So one should be careful of this of UCCSD. This is sort of unavoidable in this case, and this is what it is. And here I have tried to emphasize on UHF because in other works like in Garnett's and other works, the other groups which uses CCSD solver, they sometimes what we understand is that they try to rely on UHF to estimate the right number of particles, but this certainly can lead to problem. And the next another point is that when we do not we are in conflict that whether we have obtained the right sector. So but for theoretical analysis, sometimes we restrict the search space to a specific spin. So when we know the ED result, but we want to compare CCSD and ED on an equal footing, sometimes we have done this trick where we have restricted the search space. That is, we have kept the number of alpha and beta electrons same, so that we do not really search through a very large space, and that sort of guarantees that we reach the right particle sector. So so this behavior one should be aware of. The next is that total energy based analysis of the particle sector is also another useful analysis. This is an indicator of accuracy and also indicator of convergence with respect to the rank. So here the example I have taken is manganese oxide. This is a molecule, and here our objective was to study total energy of this molecule, because for this various benchmark results were there. So I'm not showing all the details, but what I just wanted you to focus on is that we have chosen like 3 different impurities given like this. In one impurity we have sigma, sigma star, and delta. So these are natural orbitals, and in another we have pi. Okay, so this is actually pi star. So I forgot to put star. So these are like 2 degenerate one, pi star, and for this choice, actually we were able to achieve like very good total energy when these A, B, and C are kept separated. with respect to some benchmark heat bath CI number. But here, I mean, we have studied for for the fact that how accurate is CCSD just by analyzing total correlation in by analyzing correlation energy with respect to the truncation of the couple cluster hierarchy. Here one can easily see that for impurity A, the convergence is pretty rapid. Pretty good, and for B and C as well, convergence is pretty good. But when we combine A, B, and C together, then what we can see is that for CCSD and CCSD-T, difference is pretty large. So the message it gives is that when we have really, increase, number of orbitals in our impurity, sometimes the performance of CCSD solver, gets hampered, and it's the quality deteriorates. So that was quite surprising finding to us. And another point I want to make here is that often this sort of convergence study can give like a prior indication is that whether we should like stop at what rank we should stop, like whether CCSD is sufficient or not. So if let's say the total energy convergence is as good as here, so then we do not need to go to some more accurate, more higher rank of the couple cluster hierarchy. So this total energy based analysis of this particle sector is quite important. So before going into a full-blown calculation, we often do this analysis. Prior to run the full self-energy cycle, self-energy embedding loop. So next point is that the question of thermal Green's function. So this here, let's say the definition of a thermal Green's function is can be given by this Boltzmann averaging, and here this small j means the Green's function for various particle sector, and also for various ground and excited state for particle sectors, and that can be averaged together with the weight of Boltzmann factor. And with couple cluster, one caveat is that one can evaluate the ground state Green's function, but the excited state Green's function for a particle sector, I think it's just not possible to evaluate. So that's a limitation of the formulation. So therefore, this sort of definition of thermal Green's function is almost very hard to evaluate with the current formulation. So what we do here is that for spin degenerate cases, where we know that here is the example. But what I mean by spin degeneracy is that for m number of alpha, m number of up, and n number of down, and n number of down and n number of up and m number of down, so they are of same energy. So we can just take average of them, that we always do. And in practice, one can take for many nearly degenerate particle sectors, so this averaging is possible, but this is certainly not perfect, and this can pose problem for metallic cases. So in the next few slides, I will discuss whether CCSD truncation is sufficient. So for this study, I mean, the system we have taken is the cubic perovskite in the paramagnetic phase, and which is, I mean, in room temperature, it is in paramagnetic room, and higher temperature, it exists in paramagnetic phase, where this T is the Néel temperature, and experiment predicts a gap, I mean, of 1 to 2.3 EV, but cell constant GW, as shown here, predicts, I mean, fails to, reproduce this gap, but if I mean, self-energy embedding theory with ED solver is used, it can open this gap, and we this was reported in this work, and we took this example for CCSD solver, because this is considered as quite tough problem, because I mean, various previous work could not really produce it, and it could be done. I mean, this gap can be opened only by using outer loop cell consistency. So this could be quite a good test for CCSD solver. So in the next few slides, I'll be showing results of that. And here we'll be using two impurity setup. In one, we use only T2G, and in the other, all these, I mean, the T2G, EZ, P pi, and P sigmas are considered. So first is that impurity setup A, where only T2G is considered. And so here, first with ED solver, one can see that so the gap opens, and but I mean, the value is quite small in comparison to experiment, and also with couple cluster solver, it can successfully open the gap. So this is certainly improvement with respect to cell consistent GW. So that's definitely a good news. But if we want to achieve some quantitatively good result, so then we increase the size of impurity. So then in the other impurity setup, where ED certainly improves with respect to the previous setup, but with couple cluster solver, instead of improving, we see a spurious peak near the Fermi regime. So that definitely raised concern about this, about the solver, and it requires a bit more study, and perhaps we need to improve this solver. So in order, after this observation, I mean, the approach we took is that we can definitely, I mean, the easiest possible route is that we just increase the rank of couple cluster, and then that will certainly improve the result, but it comes with a very high cost. Because if we increase if we take just one rank higher, that is GFCCSDT, then the cost goes as into the 8. And so what we have done is that we have implemented this exact solver, and also an approximate version of it, which merely scales as into the 7. So for the full version, we have the ground state parameterization is given by this, where for this amplitude we have for the T amplitude we have used singles, doubles, and triples truncation, and both, and for the n+1 and -1 as well. But in the other variant, and here it is given by the name 2,3, because here for the ground state we use only singles, doubles truncation, but for the n+1 and n-1 we use singles, doubles, and triples truncation, so that gives a scaling of into the 7. And one rationalization rationalization of this choice is that if we consider the layman representation, so there appears the projection of like various n+1 and n-1 particle states, and in this projection we have used higher higher truncation. So that means this projection is more complete in this approximate route. So therefore, it should improve. And here, I mean, there are some equivalent approximation that is used for wave function based theories, and that actually showed improvement. So this actually, I mean, this table shows that performance, and it is taken from QChem manual, and it also satisfies. I mean, this approximation also satisfies, I mean, theoretical requirement of size extensivity of the Green's function formulation. So when we study with this improved solver, what we see is that previously for p pi and eg in choice of impurities, the self energy of CCSD is quite different with respect to ED, as one can easily see here. But both CCSD and CCSDT 2-3 improve with respect to CCSD, and more importantly, there was some causality breakdown in CCSD self energy, so that is no more there, both for both these cases. And the next is that we have done a primary self-consistency study with manganese oxide. And why we have chosen manganese oxide? Because manganese oxide doesn't require this outer loop self-consistency. Only inner loop self-consistency is good enough. But for this system as well. Okay, so here our impurity with the impurity choice. When we choose the impurity like this, then CCSD actually produce a spurious peak near the Fermi surface, whereas which is not there in ED and also not in experiment, but this is certainly wrong. But when we apply this CCSDT 2-3 solver, so then actually this behavior go away. And here I have not shown the CCSD T full triples number because it also shows this spurious peak, but we are still analyzing, which is certainly not what we wanted, but this is what we see, and that probably requires a bit more analysis, but I'm not going into that as of now here. So some final remark is the Langstroth based CC couple cluster Green's function is numerically efficient and stable, and the error in particle sector search may lead to divergence in self-energy embedding theory. So one should be very careful in the first iteration of self-energy embedding theory and try to analyze this particle sector a bit carefully before going into the full self-consistency. Well, when one sees divergence, then one goes into that detail, but this is really important. And the next is that with increasing size of the impurity, accuracy and deteriorates. And this is not a good news in terms of the fact that if one wants to achieve convergence with respect to with respect to the choice of impurity, then one has to systematically increase the size. But this behavior of CCSD solver kind of precludes this sort of convergence study. So, I mean, our consensus is that with increasing rank of couple cluster, this problem or this behavior will be less pronounced. So we are yet to study that behavior, but I mean, but we will probably show some numerical data for that, whether this problem goes away. Next is that GFCCSDT provides significant improvement over CCSD truncation. So yeah, we are optimistic about this solver.
Thank you, Avijit. Does anybody have any questions?
I have a couple of questions.